Hello, once again, thanks for joining us on Space Nuts. My name is Andrew Dunkley, your host, and on this week's program, episode 306, we're talking asteroids. There are a couple of asteroids in the news. There's the one that's going to pass us by in the next few days. It's humongous. And there's another one that NASA is asking for help with, and we'll tell you why. There's also a lot of discussion on at the moment about the Hubble constant. They're trying to figure out the expansion of the universe and why it is happening the way it is and what exactly is happening. And the numbers don't stack up, but they think they've come up with a reason why. So we're going to look into that. We'll also answer some questions about white holes and gravity. That's all coming up on this week's episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me as he does each and every week without fail, because he is chained to his desk like a good public servant should be, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I'm good. And you're still around after a change of government. That's good to see.
So far, so good. Yeah. Although I'm just, as we speak, I'm just apologising for a meeting that I'm not going to be able to make, but that's not, that's because I'm talking to you.
Well, I feel very important now.
There you go. Yeah, it's an important meeting too, but not as good as this.
Yes. And before we get down to business, you fell off your bike.
Yes, I did.
You should never tell me things off camera.
No, you'd think for somebody who is interested in a topic, namely astrophysics, that absolutely centers around the phenomenon of gravity, you'd think I'd understand it, and understand that if you try and stand upright on a hill after you're trying to get off your bike, because the damn bike stand's fallen down on you, you'd think you'd get off the right side of the bike so that you were kind of facing up the hill rather than down, because down tends to keep on going, which is what I did yesterday. Dear. So I've got a very sore hip at the moment, but we're still in one piece. And
all right,
so
well,
far, so good.
That's probably just as bad as what I did yesterday. I stabbed myself.
All right, there you go. Oh.
Right on the point of the finger with a pair of scissors. I was trying to open one of the Salvo's donation buckets for the Red Shield appeal, because by law in New South Wales they have to be sealed, and we seal them with zip ties. And I was trying to lever the scissors underneath the zip tie to prise it up and cut it, and it slipped and went straight into the tip of my finger, right near the fingernail. So I lost a lot of blood. I feel very faint now.
Yes, you would. You would. Probably made a mess of everything you were trying to handle as well.
Yeah, I didn't bleed on anything but myself. I'm very good at holding back the flow. But we're all well now. We're all good. Whoever invented Band-Aids deserves a medal.
Indeed, that's right. Yeah, but it doesn't say much for our respective competence in fields that we ought to have sorted out when we're in our preschool era.
Yes, indeed. Now, Fred, let's talk about asteroids. The first one we need to talk about is asteroid 7335 1989JA, because it's going to pass the planet in the next few days. And for those who've sort of taken an extra week to listen to this podcast, it's already happened. But it will happen Friday, technically speaking. And it is a big one, about 1.1 miles across or something.
Yes, that's right. Getting on for 2 kilometers, Andrew, and that's definitely a killer one that size. The rule of thumb that the asteroid world uses, or the near-Earth asteroid world, is 100-meter asteroid is the same as a 100-megaton nuclear weapon in the atmosphere. Whoa. So imagine something 20 times that size. It's nationwide devastation, I think. An asteroid very well known, 1989 JA, that tells you when it was discovered. In fact, it was discovered by somebody that I used to know, Eleanor Helene, who was very a very prolific asteroid observer at the Palomar Observatory in California, and she spent time working at the United Kingdom Schmidt telescope that I used to be astronomer in charge of. So she came over. It would have been the late 80s when she was over with one of her students, a young man called Bobby Boss, who I think became quite famous in this world as well, in the asteroid world. So yeah, it's a near-Earth object. Its trajectory, which took it or takes it, close to Earth, is still quite relaxed in the sense that it's about 11 times the distance of the moon is the nearest that it gets. It's about a bit more than 3 million kilometers, 3.5 million kilometers, something like that. So it's not going to do anything, but it's always a salient thing to take note of, the fact that these things are charging around in our vicinity. It is classified as a PHA, a potentially hazardous asteroid. And, it's one of these objects that is now monitored very assiduously. In fact, by NASA's Center for Near-Earth Object Studies, it's very much on their horizon. So a news item that shouldn't cause any kind of distress in the sense that it's a good news story, because we know about these things now, which we didn't a long time ago when things just came flying at us from space, gave comets a bad name, gave asteroids a bad name. So that's, as I said, a good news story.
Yeah, I know. I've read a few stories about it in the popular press, and of course, a few are referring to it as a near miss or we're avoiding disaster. All those sorts of headlines to try and make you read it. I thought the funniest one though was where they were trying to make people understand how big this is. I mean, if you say 2 kilometers, 1.1 miles, or whatever number it turns out to be, people go, righto, I can see that far, but. One article reported it as being double the length of the Burj Khalifa, the tallest building in the world. Yes. Now, that's probably a fair assessment. But the one that made me laugh was the one where I think they're trying to, I don't know if it's desperation or if it was a headline they thought would just grab your attention, but 350 times the size of a giraffe.
Usually it's elephants, Andrew. So I
was out at the zoo last week and I was looking at the giraffes and I didn't kind of equate them to asteroids.
No. And these, I don't really get that, because how can you imagine something 350 times that size?
I know. That was exactly what I thought. But
anyway.
Oh, well, it got my attention, so I suppose that's why. Okay, so that's happening on Friday. Will we be able to see it?
There will be. The problem with asteroids, near-Earth asteroids, is that they move through the sky so quickly. When they're close by, and amateur astronomy telescopes, which is what you'd need to do something like that, are not really tuned usually to things going that fast. It needs a slightly different way to mount the.
I don't think I could wiggle my knobs fast enough.
Yeah, well, that's right. Yes, so it's knob wiggling. It's usually electronic knob wiggling. You need to essentially put in the coordinates. Having said that, that segues rather nicely to the next story.
Yes.
Which is a much smaller object that NASA knew was in our skies, another potentially hazardous asteroid, this one 2012 UX68. On the 15th of May, 10 days ago as we speak now, it was within 2 lunar distances of our planet. So that is in the region of 700,000 to 800,000 kilometers. And its close approach actually took place while our hemisphere was facing the asteroid, and so NASA were very keen for observers in Australia and New Zealand to to actually try and get some imagery of it, because what you need is a fix on it, its position at any given instant, so that you can refine its orbit and you can know just to the extent to which this close approach has actually altered the orbit of the asteroid. So there was an alert from NASA's JPL, and actually in collaboration with our National Science Agency, the CSIRO, which was responded to by scientists at the University of New South Wales. Actually, I think their campus in Canberra, so it's Canberra Space, which is one of their departments, and in collaboration actually with colleagues in New Zealand, and that worked out well, because the weather in Australia was pretty rubbish, as it has been for about the last 6 months.
I know.
Whereas New Zealand, they got some good observations of it. This object is much smaller than the one we've just been talking about. It is 70 meters or thereabouts, but still, big enough to be a worry if something like that impacting the Earth. Actually, you're talking about a Tunguska event, something that could demolish a fairly large area of vegetation, for example, as the Tunguska asteroid did back in 1908. Was that right?
Yeah, I think that sounds familiar.
Yeah. So it's I guess these stories are just reminding us that we live in a fairly busy part of the solar system. Space is big, of course, so that a miss is as good as a mile. But as I said before, the great news is that there is an entire industry now which is on asteroid watch, if you can put it that way. And just as a postscript to this, I've had some interesting correspondence recently with scientists about trying to get some Australian involvement in the DART mission. Remember DART? That's the Double Asteroid Redirection Test. It's a NASA probe which is on its way to an asteroid called Didymos, which is a double asteroid. And what they're trying to do is take a swipe at Didymos's moon to just change its orbit slightly, and then check what has happened, just to see basically what the effect of clouting an asteroid is. Didymos has a moon called Dimorphos, which is I think it's only a few meters across. I can't remember the numbers, but yeah, it's an interesting possibility that maybe we in Australia might get involved with some of the observations that might be needed for actually quantifying how much of an impact, how much of a move that the impact has made on the asteroid Dimorphos.
Okay, well that will be interesting. That's a very exciting project. It does also make me wonder, Fred, if we know, even with asteroids that we know about and that are documented and we know where they're going to be in years to come, what's to stop them being hit by something in the outer reaches and being knocked onto a collision course with Earth?
Yeah, well, it could happen. That's right. Usually, these things are continuously monitored to the extent that you can. Sometimes they get lost. They just go so far away from Earth that you lose them, because we're talking about things fairly near the limits of detectability, these small objects, although we've basically found things down to 10 meters in size that have whizzed by the Earth. So it's a tribute to the kind of technology that we have these days, and also to the will within the scientific community to devote resources to this, because in a sense it's civil defense. So there is a pretty strong mandate for doing that. But as I've told you before, I was on the periphery of the beginnings of this sort of study with two of my colleagues in Edinburgh, Victor Klug and Bill Napier, who were among the first to recognise that the Earth's history has been affected by impacts and may continue to do so. Yeah.
Yeah, well, we only talked about one a couple of weeks ago in China, wasn't it? Yeah.
Yes, that's right. Yeah.
All right. Watch with interest. And if you've got the gear and you're an amateur astronomer, maybe you'll be able to track 1989 JA later this week. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson. Oh, excuse me. It's very cold in my office and makes my nose run. It's weird, I know, but
That's all right.
okay. Are we ready for phase 2 of the operation?
Yes, sounds good.
Okay. Here we go. In 3, 2, 1.
3, 2, 1.
Space nuts.
Now, Fred, from asteroids to the Hubble constant. Now, this is something that I guess we need to explain first up, but there's a lot of work going into understanding this. And a 30-year Hubble study from the Hubble Space Telescope has come up with some data, but it's also created more questions. But then there's another study that seems to have potentially come up with answers to those questions. So let's start at the beginning. What is the Hubble constant?
It's the number that essentially determines what the expansion of the universe is at the moment today. It's usually called H naught, H being for the Hubble constant. The naught is a subscript, which means that it's the Hubble constant now, compared with what it might have been some time in the past. And once again, harping back to when I was a young astronomer in Edinburgh back in the 1970s and 80s, the value for the Hubble constant was one of the biggest unknowns at the time. The way you measure it, and it's the way Hubble did, was you look at galaxies and you measure their velocity of recession, how fast they are moving away from us.
Mm-hmm.
But then you've got to have another indicator that tells you how far away they are, because it's by the Hubble constant essentially relates that expansion velocity, the recession velocity of a galaxy, with its distance. The further away it is, the faster it's moving away from us. And so the trick is finding the means to measure the distance. And the standard yardstick for that are a set of variable stars, which are called Cepheid variables, whose light varies in a way that we understand very well, and we know what their intrinsic brightness is. It goes up and down, but you can take an average and we know what it is. And it depends on what's called the period of oscillation of these things, how regularly what the interval is between one maximum and the next. That's basically how they work. So that fairly complicated set of work led to, in the 70s and 80s, to two quite different estimates of the Hubble constant. There were two opposing groups, very, very polarized. One of which, if I remember rightly, led by Alan Sandage, said it was about 50, and I'll say a bit about the units in a minute. And the other one, there was a fairly big group. I think Gérard de Vaucouleurs was one of the astronomers in that group, and there were others too. The names will come to me in a minute. They said it was 100. So you had these two values, 50 and 100, yeah, differing by a factor of 2, with two groups swearing blind that was the answer. So what was the remedy to try and solve this conundrum? Well, it was build a space telescope, which was eventually launched in 1990. We call it the Hubble Space Telescope, and that's why it was built, essentially to resolve this issue by making very, very accurate observations of these Cepheid variable stars in not just our galaxy, not just the neighboring galaxies, but ones that are relatively distant. And, by the turn of the millennium, that had been done. And the various teams, I think there were 2 teams that looked at it, probably, inheriting the mantle of those earlier 2 teams from the 1970s. And they reached a consensus that the Hubble constant was known then to an accuracy of 10%. And the answer was 72, which is pretty well halfway.
Not 42.
No, it's not 42. But it's, if you take the average of 50 and 100, you don't get far off 72. It's 75. So 72 plus or minus 8 kilometers per second. What are the units? something a little bit abstruse. They are in kilometers per second per megaparsec. Now, a megaparsec is essentially 3.2 or thereabouts million light years, because a parsec is the unit of distance that astronomers use. We don't really use light years, although light years are a very convenient way of expressing distances. One parsec is the distance of an object that has a parallax of 1 arc second, hence the name, a parsec. And it's what you actually measure, because parallax is something you determine by the Earth's orbit around the sun. So 1 parsec turns out to be roughly 3.2 light years. And so a megaparsec, a million parsecs, is 3.2 million light years. And what the Hubble constant means, 72 kilometers per second per megaparsec, it means that for every megaparsec further out you go, the recession velocity, the speed that a galaxy is disappearing, increases by 72 kilometers per second.
Okay.
So that's essentially the Hubble constant itself.
Right.
Now the plot thickens.
Yes.
Because first of all, there have been more researchers which have narrowed that number down even more. Remember, early 2000, 72 plus or minus 8 kilometers per second. By now, because of additions to the telescope itself, actually, there were new cameras that were implemented. We've got a new value, which is even more accurate. The current accepted value is 73 plus or minus 1 kilometer per second. So you're down to almost a 1% error. And that it's actually really interesting because once again, harping back to Edinburgh, my boss in those days was the Astronomer Royal for Scotland, Professor Malcolm Longair, a Scotsman, actually the first Scotsman to be an Astronomer Royal for Scotland. They were always from somewhere else before that. And I remember him saying, this would have been before the Hubble telescope was launched, we are on the verge of a new era of precision cosmology. In other words, high precision cosmology, because it was all hand waving stuff before that. And now we've got 1 kilometer per second accuracy. So good old Malcolm, his words were correct. That's a terrible impersonation of him, I have to say.
I thought it was pretty good, actually.
I hope he'd forgive me. He's a very inspiring person to work with. He was my PhD supervisor, actually. It's terrifying. Anyway, that is a different story. But yes, he was right. We were on the verge of an era of precision cosmology, and the Hubble constant tied down to 1 kilometer per second by, the work on the Cepheid variables. But
I knew there was a but coming.
There is a but. Yeah. Where's the but? It is the fact that there are other ways of measuring the Hubble constant, and they involve looking at the cosmic microwave background radiation. That that sphere of microwave radiation that surrounds us, that we're at the center of. And what we're seeing there is the echo of the Big Bang. And that, when you analyze that, which you can do by looking at the slight temperature variations throughout the cosmic microwave background radiation, 1 part in 100,000 temperature variations, tiny ones. It's been done by a number of different satellites, the most recent of which is the European Space Agency's Planck spacecraft, which really sorted out the details and gave us the best analysis of that cosmic microwave background. When they do their sums, they get a different answer. They get a Hubble constant today of 67.5 plus or minus 0.5 kilometers.
That's a big difference.
Per megaparsec. It is when you consider what the error bars are. That's right. Yeah. So it's a significant difference given those error bars, and that is the current conundrum. That's the problem, and it is engaging cosmologists in a big way. This anomaly, the Hubble constant anomaly. There is one piece of research that is really just been released. I think within the last 5 days, actually. It's in a press release from the University of New Mexico. And It's about scientists these are theoretical scientists, University of New Mexico, very, very clever people who build models of what the universe is doing. And they have reason to believe, and it's basically, to do with mathematical transformations. So we've got some esoteric stuff from the mathematics that we hope will relate to the reality of what's happening in the big universe. And what they've done is they've kind of identified something called a scaling transformation. This is it's a mathematical entity that's part and parcel of what we're looking at. But it turns out that these things are symmetrical, these scaling transformations, and they've essentially opened a new path, I guess is the best way to put it, to looking at some sort of entity, which they're calling a mirror world or a mirror universe, that might explain this discrepancy. Now, I am, as you can probably tell, Andrew, I haven't read enough about this yet to get the details, but the idea of mirror worlds is appealing because that's at the heart of supersymmetry, which is the idea from particle physics that there's a whole array of subatomic particles which have supersymmetry with the normal particles that we know about, but which we don't see because they're hidden in higher dimensions and things of that sort. So I'm going to I'm going to quote from SciTech Daily because they've got a very nice, a really nice kind of one paragraph summary of what's happening, which I'll read. If the universe is somehow exploiting this symmetry, researchers are led to an extremely interesting conclusion that there exists a mirror universe very similar to ours, but invisible to us except through its gravitational impact on our world. Such a mirror world dark sector would allow for an effective scaling of the gravitational freefall states while respecting the precisely measured mean photon density today. And so that plays into, because the photon density is what comes out of the cosmic background radiation. One of the scientists who's been involved with this says, it's nice to be able to quote them, in practice, this scaling symmetry could only be realized by including a mirror world in the model, a parallel universe with new particles that are all copies of known particles. The mirror world idea first arose in the 1990s, but has not previously been recognized as a potential solution to the Hubble constant problem. This might seem crazy at face value, but such mirror worlds have a large physics literature in a completely different context, since they can help solve important problems in particle physics. There you go. Supersymmetry, I guess, is what is being referred to. Just the final sentence. Our work allows us to link for the first time this large literature to an important problem in cosmology. So great stuff.
I suppose when you can't, when you've got a variable between the estimates for the Hubble constant, and you can't find a physical answer for it, you have to go to theory. You have to go to modeling.
Yes. So what's wrong with our models? What are we missing exactly?
Yeah,
and that's the way astrophysics works.
Yeah, I also think that this is going to start people asking about dark matter and dark energy. Are they part of the equation as well?
Indeed, they are, and that's because supersymmetry, certainly for dark matter, supersymmetry is one of the great hopes for our understanding of it. Although it's been totally elusive in the particle physics world so far, they haven't cracked it at CERN. They've sort of almost given up on the chase because they don't think they've got high enough energies at CERN to detect supersymmetry. But I think it's still on the agenda. And what an interesting tie-up, though, between the dark matter problem and the Hubble constant problem. Maybe it'll all come together in some magical new theory that we'll be celebrating at the end of the year.
I was about to suggest that. Definitely worth keeping an eye on.
Thank you.
If you want to read the article, it's on the SciTech Daily website. So you look for what's the title of the article? Ghostly Unseen Mirror World should get you there. This is Space Nuts with Andrew Dunkley and Fred Watson. Okay. Now we've got a couple of questions. How are we going for time? Yeah, we're going all right.
Yeah, sounds excellent.
Now I've just got to remember what they were. Okay, that one, and I'll get rid of that one. We'll do that next week.
Excellent.
Okay. All right.
Everybody's sending in their questions.
Yeah.
We must do some text ones sometime as well, because I think
I haven't received any lately, but
okay.
Yeah, there will be. Hugh's listening, so he'll be able to sort some out for us. But I do get some on Facebook and things like that, which I really need to compile in a better filing system so that I don't forget about them, because they get lost in my email when I send them to people. Okay, are we ready?
As ready as we're ever going to be.
All right, final segment in 3, 2, 1. It doesn't want to fire, which is a bit of a worry. Hang on, what I'll do. Okay, I'll try that again. Sometimes you've got to switch it out of live mode into preview mode and then back again, and it'll wake it up. Not this time. See, Hugh, now that you've actually got to watch this happen, it sometimes just doesn't want to play ball. All right, let's do it the old-fashioned way. Oh, no, that won't work either, because I've got everything going through my headphones. All right, I don't know what I'm going to do. You wouldn't have heard that, would you?
No, I didn't.
It works in preview mode, but it won't go in live. All right, here we go again. One more try. No. Okay, we'll skip it. We're going to just have to add a link in there, intro in there, Hugh, when we go into the production mode. All right, well, hopefully I can get the questions to fire, but I'm starting to have my doubts. 3, 2, 1. Okay, Fred, let's see if we can answer some questions from the Space Nuts audience. And one of our regulars is Rusty from Western Australia. And that ain't going to work. All right. Here we go. Now, what I might have to do, and this could cause trouble because I've got it on headphone mode, and if I switch it to speaker mode, that may well solve the problem, but it also might cause a foldback issue. So let me find these. Okay, I'll disconnect my headphones and see if we can do it this way. The old-fashioned, back in the 60s radio, hold the speaker to the microphone routine.
Yep.
Roger, you're loud and clear here also.
Space Nuts.
All right, I'm going to do that again because it wasn't loud enough. And then I can quieten it down.
Roger, you're loud and clear here also.
Space Nuts.
Okay, Fred, let's see if we can answer some questions. And the first one comes from Rusty, our old mate in Western Australia.
G'day, Fred and Andrew. It's Rusty in Donnybrook. I hope, Fred, you're 100% now after your COVID adventure, and Andrew, you missed out on catching it. So my question is about white holes. Black holes are supposed to be dimensionless. What about white holes? Are they supposed to be dimensionless as well? And if they're not necessarily dimensionless, could we be looking at the inside of a white hole when we look at the universe? That's it. Thanks very much for a fantastic show, guys. Cheers.
Thanks, Rusty. Great to hear from you again. Hope all is well in WA. And yeah, white holes. Well, first of all, we need to point out that we've never seen one. We don't even know if they exist. But if they did, Fred, would they be dimensionless?
Yes.
Oh.
Because so what's a white hole? Exactly as you've said, Andrew, they've never been observed, but they are a theoretical possibility that comes out of the equations for a singularity, which is what a black hole is, a point in space of infinite density. And it's dimensionless, so that's why its density is infinite. There's no dimensions. So what leads to the idea of potentially a white hole is that if you in the equations for relativity that determine the behavior of a singularity, if you reverse I think it's time, the parameter time, if you make it negative time instead of positive time, what you get is something that's the opposite of a black hole. You get something from which everything escapes, but nothing could go in. Now, where it's escaping from is a really interesting idea. But yeah, stuff comes out of it, but nothing can go in. So it's defined as being the same, the same as a black hole. It's a dimensionless point, but it's got this swap of the time direction in the equations. Now, the second part of Rusty's question is really interesting, because if you plonk yourself in the middle of a universe that's actually a white hole, stuff's leaving it, I'm not sure that you would be able to tell the difference whether you were in the center of a universe made of a giant white hole compared with a giant black hole, because in both cases you've got this curious gravitational singularity. People have suggested that our universe has an event horizon like a black hole does, but in our universe we're looking at it from the inside rather than the outside.
Yeah.
And it's my understanding that a white hole would have an event horizon as well, but of course it will be white, hence the term. And we've never seen one, which leads, I think, most cosmologists to the idea that they probably don't exist, that there'll be some physical reason why this mathematical entity cannot be brought into reality.
I remember a particular Star Trek episode back in the day of the original TV series that Gene Roddenberry wrote, and I think, did they go through a black hole and come out the other side, and it was a white universe with black stars? I distinctly remember that.
Yeah.
The total opposite to the reality that we know. And, I guess that's what a white hole is technically supposed to demonstrate, the absolute opposite to a black hole in every respect. But you've got to ask yourself, how could it exist rather than does it exist?
Yeah, that's right. Just going back to that, though, in a way, that's what if your eyes were sensitive to microwave radiation, that's what the universe would look like.
White.
A white universe, yeah.
Oh,
because
wow.
you'd be seeing the cosmic microwave background radiation.
Okay.
It would be pretty faint, but that's what it would look like.
Gene Roddenberry was pretty darn clever, wasn't he?
Oh, yeah, very much so.
Of course, if you were standing outside our universe, and you'd have to run very fast to keep away from it because it moves so quickly, it would be beige.
It would be beige, yeah, that's right. You'd need to be running at, 72 kilometers per second per megaparsec to keep out of the way.
At least. At least, yeah. Well, you'd be right. You've got a bike.
I've got a bike, yeah. Not very well controlled at the moment.
All right. Thanks, Rusty. Good to hear from you. Let's move on to our next question, and it'll be the final one for this episode, from Cameron.
Hey, Fred and Andrew. This is Cameron from Arizona. I had a question about gravity. So you look at the gravity field around the moon or planets or anything, and it's not uniform, right? There's gravitational anomalies. When you look at things like temperature, though, the zeroth law of thermodynamics says temperature should eventually become in equilibrium with each other, right? You put two bodies of different temperatures next to each other, they'll eventually come to the same temperature. Does the mechanism or a law like that exist for gravity? Should we expect that gravitational anomalies on a planet would eventually even themselves out over time? Thanks. Love the show.
Wow, that's a really deep question. I don't think we've ever been asked that
No, we
before,
haven't.
or anything similar to it. It's that's way out of left field, but I like it.
Yeah, it's great stuff, and yeah, it always. Again, I'm sorry, I'm in nostalgia mode today, obviously, but going back to the '60s and the Apollo missions, the precursors to the Apollo missions, the fact that these gravitational anomalies were identified on the moon, they were called mass concentrations, because you can tell from the orbit of an orbiting spacecraft what the gravitational potential is underneath you, and it was because of that the movement of the spacecraft tracked very accurately that you could work out that there were these mass concentrations. So mass cons was something that were talked about a lot in the Apollo era. They've now been mapped since by the is it the Grail? Grail is the pair of spacecraft that were in orbit around the moon to sense the Gravity Recovery and Interior Laboratory. That's what the acronym meant for. Two spacecraft, and the distance between them being measured to a micron or something, and that's how you can track the gravity anomalies. So we do know about those things exactly as described. That objects like the Earth, we've got very strong gravitational anomalies, which are kind of movable feast because a lot of it comes from melting ice in the Arctic and Antarctic. But relating it to the way temperature equilibrates between hot and cold objects, is that there are analogues actually, and I guess what we're talking about here is a kind of allegorical thing almost, because the reason why temperature, if you've got temperature variations in something, the reason why they iron out to become the same is because of one of the heat exchange mechanisms. And for example, it might be, if you've got a piece of wood or something like that, which is hot at one end and cold at the other, wood's not a very good thermal conductor, so it would take a long time, but eventually the thing would come to equilibrium because of the conduction of heat through the wood. Happens a lot faster with metal, and we all know about those things. So we know about those various mechanisms for heat transfer. With gravity, though, the gravity is symptomatic of well, exactly what we've been talking about: concentrations of mass. For the gravity to even out, it would have to mean that the concentrations of mass evened out. And that would probably happen over very long periods of time. If you've got a world, well, think of the Earth with the concentrations of mass underneath. Some of that comes from magma plumes and things of this sort, stuff going on in the Earth's mantle. Over long periods of time, as that mantle cools, the temperature probably would become even. But it's because because of thermal conductivity, again, because of stuff equilibrating, then that would remove the mass concentration, so it smoothed out gravity. But it's not gravity itself that's being smoothed out, it's the mass that's causing that is being redistributed, if I can put it that way.
Okay, right. So the answer is no.
Yes. well, it's yes, but it's not gravity. It's stuff on, the stuff that's causing gravity.
Gotcha. Righto.
So yes.
Hope that helps, Cameron.
Yeah. Thanks, Cameron. Great question, though.
Oh, fabulous question.
Yeah. Lovely thinking there.
I saw a really good demonstration, I think it was on TikTok the other day, of gravity. I mean, everyone thinks of TikTok as young people dancing, and that's about it. There's a lot more to it. They have some really great bits and pieces of lectures, and I've started following a few people in the scientific and astronomical world, and they did a great demonstration of gravity the other day. They had a piece of black lycra stretched out dead flat and they rolled marbles across it. And they said, that's a universe without gravity. Then they
Yep.
put a ball in the middle of it, and it
Yeah.
sunk down, and that was the sun. And then they
Yep.
started rolling the marbles, and they spun around it.
In
And
orbits.
they said that's the influence of the sun's gravity on the planets and the moons, for example. And they said, now we know you're going to ask the question as to why Earth doesn't fall into the sun like the marbles are. And the answer to that question, which I thought was brilliant, was because out there, unlike on here, there is no friction. Therefore, it doesn't spiral into the sun and disappear. It will one day, if it lasts long enough. But I think the sun will probably destroy itself before that happens. I think the timing of the function of our solar system won't work to a point where we'll get sucked into the sun. It will come over us instead. I think, is that right?
Yes, that's right. Yeah, we are actually moving away from the sun slowly.
Yeah, it was a
It's,
really good demonstration, though, because
yeah.
it, and I suppose you could expand on it by putting different sized objects on the lycra, so it shows the different influences of of gravity, which varies, as we know, due to the mass of objects.
Yeah, what's really nice about that, Andrew, is that it absolutely demonstrates one of the fundamental principles of relativity. So yes, you've got, the heavy thing in the middle that's distorting the lycra, and the marbles follow curved paths around it. As far as the marble's concerned, though, it thinks it's going in a straight line, but it's the space that it's moving over that's bent. And
Yes.
That's the really neat bit. These geodesics, as they're called.
I wish I'd known that 40 years ago when I started playing golf, because that's exactly the same effect that I have with putting.
Yes. Yeah, your straight line is a little bit different from what the Earth wants to give you, I guess.
Yeah, very true. And there's a few other factors in there, like wind and the way the grass grows. You've got to take all that into account.
Absolutely.
But that's a different story. But I just thought it was a fascinating demonstration, and it really simplified the way gravity acts on things. Yeah. Now, just a reminder too, if you want to send us a question or send us a comment or just want to make a political statement, you can send it to us via our website, spacenutspodcast.com. And you can click on the AMA link. You can send us text that way or a voice message, or you can click on the right-hand side. There's a little tab there, which has vanished off my screen right now. There it is. Send us your voice message. So that's how you can ask us questions or just send us voice messages. Some people just send us messages for the sake of it, or just want to make a comment about things, which is fine. We use them from time to time. And while you're on the website, check out the Support Space Nuts button and learn about becoming a patron. There are all sorts of ways of doing that, and we're updating the information regularly. So if you are keen to support us in a financial sense, you can do that, and there are several options, right down to buying us a cup of coffee, which I love. I'm going to go and have one in a minute. And there are don't forget to put reviews through as well. We really appreciate the people who've put in reviews for Space Nuts on their podcast platforms, whichever one you use, because the more reviews, the more attention we get, the more people that join us, the bigger the Space Nuts family gets. And we'd love to have more and more people come across and listen to the show. There's also the Space Nuts shop and also all sorts of other information in there if you'd like to check it out at spacenutspodcast.com or spacenuts.io. Okay. Fred, thank you so much. That wraps it up for another week, episode 306, I think it was. Yeah. Numbers are racking up, aren't they?
Certainly are. We're going to be on 400 before we know where we are.
Oh, yes. What do we do for that one?
We'll
start planning now.
Start planning now. That's right.
Yes. All right.
Very
Thanks,
nice.
Fred. We'll see you next week.
Sounds great. Thanks, Andrew.
That's Fred Watson, astronomer at large, part of the team here at Space Nuts. And thanks to Hugh in the studio, who does whatever Hugh does. I don't really know, but we appreciate it anyway. And from me, Andrew Dunkley, thanks for your company. I hope you can join us on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.
Okay, that wraps it up. Thanks to everyone who watched us live. Thank you. Appreciate it. And we'll see you next time. Uru.